Hey everyone, and welcome to The Explainer. Today, we are diving into what is, no exaggeration, the single biggest upgrade in the entire history of the internet.
So let's kick things off with a pretty huge question. What would happen if the internet literally ran out of room? I mean, it sounds kind of crazy, right? But the original addressing system, the one that got the whole thing started over 40 years ago, well, it's really starting to show its age. Yeah, that original system is called IPv4. The best way to think about it is like the very first highway system for the internet. It was revolutionary for its time, but now, that highway is stuck in a permanent, gridlocked, bumper-to-bumper traffic jam. So, back in the day, IPv4 had these really strict but simple rules. You can kind of think of it like the DMV for the early internet. Every single device, your computer, whatever, needed its own unique license plate. That's its host ID. It also had to know its local neighborhood, right? Which was defined by something called a subnet mask. And crucially, it had to know the exact on-ramp to get onto the main internet highway. We call that the default gateway.
So, as we started to see the writing on the wall, that we were just plain running out of these addresses, engineers, being the clever people they are, came up with some really smart workarounds to try and manage all that congestion.
And the big one is called Network Address Translation, or NAT for short. Now, this is a brilliant idea. It basically works like a private, gated community. Inside, all the houses have their own local street numbers, right? But when they want to get out onto the main highway, they all have to go through a single public exit. Your home router, that's the gatekeeper. It's constantly translating between your private internal address and the one single public address that the rest of the world see. And here you can see how it works. The NAT router is basically acting like a concierge at a hotel. It keeps this little table, a list, that tracks which specific device inside the network is talking to the public internet. It just translates those addresses back and forth on the fly, making absolutely sure the right data gets back to the right computer.
Okay, but then they made it even more powerful with something called PAT, or Port Address Translation. This doesn't just translate the address. It assigns a unique port number to every single conversation. So think of it like this. Not only do you have one exit to the highway, but now every car is given its own numbered parking spot right at the on-ramp. That way, the router knows exactly who is coming and going at all times. And if you look at the router's table now, you'll see it's tracking both the private IP address and that specific port number. It's a pretty simple addition, but this is the magic that allows all your devices, your phone, your laptop, your smart TV, all of it, to share one single public IP address at the same time. But let's be real, these were just really clever patches on a system that was fundamentally running out of road. For the kind of global internet we have today, and the one we're building for tomorrow, we needed to stop patching and just build something much, much bigger.
And that solution, that brand new superhighway, is Internet Protocol version 6. You'll hear it called IPv6. It's not an upgrade, it's a complete replacement for that old, aging IPv4 system, and it was designed from the ground up to solve the address shortage permanently.
And when I say bigger, I mean the scale of this is it's kind of hard to wrap your head around. With IPv4, we had about 4.3 billion addresses. Seems like a lot at the time. With IPv6, we're going to 340 times undecillion. That's a 340 with 36 zeros after it. I mean, it's just a completely incomprehensibly vast number of addresses. We will literally never run out.
But this new superhighway isn't just about more space. It comes with some incredible upgrades baked right in from the start. Things like auto-configuration, which means your devices can pretty much get online automatically without you doing anything. And it has enhanced security features built in from day one, which, believe me, were kind of an afterthought in the original system. Okay, so how do these new addresses actually work? What do they even look like? And what really makes them so different?
Well, IPv6 breaks it down into three main types of addresses to get traffic where it needs to go. First, you've got unicast. That's for simple one-to-one communication. Like when you're browsing a website. Then there's multicast, which is for one-to-many. Think of streaming a live video to a bunch of subscribers at once. And finally, there's anycast. This one's really cool. It's a one-to-nearest kind of deal. It sends your request to the closest server to you, which can make things a whole lot faster. And if we drill down just into unicast, there are a few key types you should know. You've got link local addresses, which are just for devices on your home network to talk to each other. They can't go out on the internet. Then there are unique local addresses, which are kind of like for a company's internal private network. And then, of course, you have global addresses.
These are your public-facing addresses for the whole wide world. Now, I mentioned auto configuration earlier, and it's honestly one of the best features of IPv6. There are two main ways it works. The first is called stateless. Here, a device literally just listens for the router's announcements and configures itself. It's that easy. The other method is called stateful. And this is a bit more like what we're used to, where the device actually requests an address and other info from a server, but it's using a new and improved protocol that's built specifically for the world of IPv6. So, here's the biggest challenge of all. We can't just shut down the old IPv4 highway overnight. That's just not possible. Both of these systems have to live together, side by side, for years to come. And that means we need some really effective ways to build bridges between the old world and the new. And one of the key technologies for doing that is something called tunneling. The best way to picture this is to imagine you have a brand new, super fast IPv6 compatible car, but you need to drive it across the old, crumbling IPv4 highway. So what do? You put that car on a special flatbed truck, an IPv4 truck, and drive it across. That's what tunneling does. It wraps up the IPv6 data packet inside an IPv4 packet to help it make the journey. And you can see here the process really does work just like that analogy. The IPv6 packet gets encapsulated or wrapped up, travels through that IPv4 tunnel on the internet, and then once it gets to the other side where there's an IPv6 network, it gets unwrapped and goes on its way. Pretty clever. Now, besides just basic tunneling, there are other methods. A really common one is the dual stack approach, where devices just learn to speak both languages. They can handle IPv4 and IPv6 at the same time. There are also more advanced tunneling protocols with names like 6to4 and Terado, and these were designed to solve some really specific, tricky problems, like how do you get this new IPv6 data through all those old firewalls and NAT routers that were only ever built for an IPv4 world? All right, so finally, let's switch gears and look at the actual tools of the trade. What do network engineers use to check the traffic and see what's going on both of these highways, the old and the new? Well, when it comes to troubleshooting, engineers have this whole powerful toolkit of command line tools. And with these, they can do pretty much everything, from just checking a computer's address all the way to mapping the exact route a piece of data takes as it flies across the internet. Let's take ipconfig, for example. This is like the first thing you type. It's the go-to command to just quickly see all the important IP configuration details for your computer. What's its address, what's its subnet mask, and what's its default gateway.
Then you've got ping. It's so simple, but it's absolutely essential. It's basically you shouting, "Hey, are you there?" across the network to another computer. If you get a reply, you know the connection is alive and well.
And last but not least, tracert or traceroute. This is like your network's own GPS. It literally shows you every single hop, every single router your data passes through to get to its final destination. It's incredibly useful for finding exactly where a connection might be slowing down or even failing completely. So there you have it. We've gone on this journey from a really crowded old highway that we kept patching up with clever workarounds, all the way to this vast new digital frontier with practically limitless space. It really leaves you with one big question, right? With all this new room to grow, what incredible new things are we going to build next? Hey, if you found this whole explainer useful, do me a favor and be sure to subscribe. We do deep dives like this all the time into the tech that really shapes our world. Thanks for watching.